Although we know that the sine wave produced by the spark gap transmitter decays after every spark, we know that the frequency, that is the radio frequency, is approximately sinusoidal at least for a while. Now the question is, how can we receive it? How can we pick that up? Well, during the time of Marconi, a device called a coherer was used, and I'm not going to say too much more about the coherer than what I'm about to say. A coherer was a device encased in glass containing two electrodes with a bunch of little metal particles between it. And some scientists at the time had discovered that when this device was excited by radio waves, that the resistance between the two electrodes would change. That is, the little particles would either cling together more or less depending upon whether a radio wave was present or not. In other words, the presence of radio waves would affect the resistance of the coherer. And when you can change the resistance, then you can change the voltage, and this is how the coherer detection worked. Now that's not the kind of circuit that I'll be describing today, because using diode detection is a lot better. On the screen right now, you're seeing the circuit diagram of a very simple radio receiver. Now this radio receiver will not only be able to receive the transmissions from a spark gap transmitter, but it can actually decode any modern AM radio transmission. In other words, this is a full and complete AM radio. If you built it, you would be able to hear music in the headphones if the radio station were transmitting music. As we analyze it, we'll think more about the spark gap transmitter, but in fact it's a really truly complete radio, and it has four parts. First of all, it has an antenna, and to make this circuit work, the antenna has to be long. I'm holding an antenna now in my hand, and let's consider why a long antenna would work better than a short antenna. When the radio wave hits the antenna, it causes the electrons to bounce up and down or move up and down in the antenna. And when they move up, the electrons bunch up at the top of the antenna, and when they move down, they bunch up at the bottom of the antenna. Now when electrons bunch up together, they repel one another, so that makes it difficult to do. A longer antenna allows the electrons more freedom of movement, if you will. A longer antenna also intercepts more of the radio wave, so there's really two reasons why a long antenna works better than a short one. The second component that you're seeing is a germanium diode, and I'll describe in a few moments why a germanium diode is better than a silicon diode. The third component that you're seeing is an earth ground, and it's important to note the difference between this ground symbol and the one that you might be more familiar with, the triangular symbol, which is just a reference point on a circuit diagram. This is truly an earth ground, and the 3 or 4 lines that I have drawn here in the circuit diagram represent plates actually dug into the earth. Earth ground is important because it provides a good source and sink for electrons. I just mentioned that if you have a short antenna, electrons tend to bunch up at the top of the antenna and bunch up at the bottom. Well, if you have a good earth ground, it prevents the electrons from bunching up at the bottom. You can just send them down into the earth and pull them back up out of the earth. The fourth component that you're seeing in this circuit diagram are the high impedance headphones. Now I'm holding some in my hand right now. A modern earpiece, for example, something that you might have with an iPhone or a modern smartphone, is not a high impedance earpiece. The typical impedance of a modern earpiece would be something on the order of 4 ohms or 8 ohms. It's very low. Now, the impedance of the headphones that I'm holding now is something on the order of 2,000 ohms or 2 kilo ohms. Now, that difference is important, as we'll see in a moment. These headphones were manufactured in the US in the 1920s. It's kind of interesting to see what it says here on the back. It says Alnico Magnetic, CF Cannon Company, Springwater, New York, made in the USA. It's interesting because in the 1920s, evidently the insulation for wires was different. If you take a look at this cable, it has beautiful cloth insulation, and I think it's really interesting to see how the standards have changed over time. The way the cable is also plugged into the radio is also rather different than what we might see in modern systems. Now that I've introduced the 4 components of a basic radio receiver, in the next video we'll take a closer look at this circuit in order to get an understanding of why that diode is really needed.